Our technique of integration using substitution, which we've seen a little bit of in extension 1, let me talk about the non-standard integrals. Call them that because they're not actually on the reference sheet. Doesn't mean you can't use them, just means they're not going to give them to you. So if you know them, you can save yourself some time. I mentioned this one the other day. The u on root u is 2 root u. Okay. It will come up a lot, well worth remembering. Du on u squared minus 1 on u. So those two in particular, when we're looking at some of our partial fraction questions and quadratic denominators, we see these a lot. Log x is x log x minus x. Tan log of sec, or if you prefer, minus the log of cos. Now, these ones here. Once upon a time, they used to be on the reference sheet. Don't know, fell out of favour, why they're not on there. The first one here, the sec-tan, probably when we did a topic called conics, was used a lot. Not so much anymore. But actually going back the other way, the derivative is well worth knowing. You differentiate sec, you get sec-tan. So consequently, if you integrate sec-tan, you get sec. The next two, the square root of x squared minus a squared and the square root of x squared plus a squared. Again, I don't know why they're not on there. Look at the answers and they're very similar. They both turn out to be logs. If you have a look at the third part, it matches whatever's in the denominator and it's x plus that. So log of x plus whatever that square root sign is. Now the difference with extension 1 and extension 2, in extension 2 they may not give you the substitution to use, which can be good too, because if I look at this one I can see, derivative times function. If I wanted to do it by a substitution, usually I'll go, well, what's causing me the problem? And the problem is this x squared plus 4 under the square root sign, and very often it's going to be whatever is to some power, which in this case is x squared plus 4. So that's usually a good point to start. Let's try it. U is x squared plus 4. There it is. We've got that under the square root sign. That was the whole point of doing it. It gets two terms, pulls it into one term. The u becomes 2x dx. Well, we've sort of got that. We've got half of it. We can now make it a much simpler integral. So u to the power of a half. Add 1 to the power over the power. Substitute back in. Wow. Mere mortal answer. Super mathematician answer. X squared plus 4 root x squared plus 4. Of course, another way you could do it is this. Not suggesting that I would do it this way, but it does work. If you see a square root and it's a sum of difference of two squares, well, maybe you could take advantage of your trig identities. So what would happen if I made x equal to 2 tan theta? Which means my derivative, or dx, becomes 2 sec squared theta. And I could substitute in. So x is 2 tan theta. Square root of x squared plus 4 becomes 4 tan squared theta plus 4. But tan squared plus 1 we know is sec squared. So I've got the square root of 4 sec squared, which is 2 sec. Dx is another 2 sec squared, so I end up with, all up, 8 sec cubed. So I now have 8 tan theta sec cubed theta. Right. Now, what I do is this. Well, I'm not quite sure how to do that, so I'll change everything to sine and coses. I now have sine theta over cos to the power of 4. Hang on, sine derivative of cos. I have derivative on. But if I didn't see that, I could do yet another substitution. How about I make u equal to cos theta now? Which means du is minus sine theta. I now have minus 8, the integral of du on u to the power of 4, which I can integrate, sub back in. There you go, 8/3 sec cubed theta. Oh, hang on. Sec cubed theta. Theta was what I introduced. I've got to get this back to x's. How do I do that? Well, let's draw myself a little triangle. We said x was 2 tan theta, so I could draw up a triangle. There it is. The tan ratio is x on 2, which means the hypotenuse is the square root of x squared plus 4. Not a coincidence that it happens to be the same third that we started with. But now I can read off that triangle what sec theta is and substitute it in. And that was the same answer we got before. Okay, probably not the best way of doing it, but there are other substitutions you could use and eventually come up with the same answer. But rather than doing substitution, remember, keep your eye out for that. Is it simply derivative times function, which this one was. See, x Well, the derivative of x squared was 2x. I could have simply looked at that and said, oh, derivative times function didn't need a substitution. This one's a bit different though. X times the square root of x plus 1. Well, it's that square root that's causing me the problem. How about this time, instead of just doing u equals x plus 1, I'll make it the whole of the square root. Playing around with that, I get x equals u squared minus 1, which means dx is 2u du. I can now substitute straight in the x, well that's u squared minus 1, root x plus 1, that's u, and the dx is 2u du. There's my integral, u to the power of 4 minus u squared. Add 1 to the power over the power, substitute back in, and well, I've factorised and played around with it, but there's our final answer. So I could have done u equals x plus 1, that would have worked as well, but it's just a different idea. Let's make it the whole square root rather than just a bit under the square root itself. How about this? I could have done algebraic manipulation. I want to create x plus 1 or a multiple of it or its derivative out the front. So if I rewrite that x as x plus 1 minus 1, then break it up into two things. And there is our x plus 1 to the 3 on 2 minus x plus 1 to the half. Add 1 to the power over the power, and we get our same answer. Do that way. Woo! dx on 1 plus root x all squared times the square root of x. What's causing me the problem? What's in the grouping symbol there is 1 plus root x. That's a good starting point. U is 1 plus root x, which means I end up with du being dx on 2 root x. Yep, I can manipulate this. Oh, but the limits, remember those limits are for x. We need to change those. That gets me 2 and 3. And, oh, that comes out quite nice. Look at that. du on u squared. This note here. It's important to separate your variables before you substitute. What do I mean by that? If you had decided to work it out and go, well, dx is 2 root x du. Okay? So you get something like that. You could multiply and go, oh, let's just substitute in for the dx. Because you're substituting in something that has both x and u. That's what I mean by separating those variables. They shouldn't be together in the same part of the integral. So you should not see an integral where there's both an x and a u. Remember, it's a complete substitution. Not just, oh, just substitute into this bit. It's a complete substitution. So if your new integral is du, remember your limits also must change. So now our one here, they're changed to 2 and 3. All right, let's do our integration. We get the minus 1 on u, substitute in, there's our answer. Sine to the power of 5x times cos x. Well, it's that sine x that's causing me the problem. It's to the power of 5. I'll go u equals sine x, so du is cos x dx. The limit's going to have to play with those. Pi on 3 becomes root 3 on 2. Pi on 2 becomes 1. It's just u to the power of 5. Add 1 to the power over the power, substitute in. But again, it's in that situation of derivative times some function. If you spot that straight away, then you don't have to worry about all the substitution. You can just go, look, I've got derivative times function. Add 1 to the power over the power. X dx on the square root of 25 minus x squared. Now, again, I'm looking at this. The first thing that hits me when I see it is x, derivative of x squared is 2x. So I know I could do it that way. If I did it by substitution, all right, what's in the grouping symbol? 25 minus x squared. That's probably what I'm going to use. The u is minus 2x dx. Play around with the limits, change them, substitute in. Oh, there's that du on root u. 2 root u when we integrate that. So I just have the square root of 16 minus the square root of 9, 1. What about if it's this by itself? How on earth could I create the derivative there? But that comes back to that idea I was talking about before. See, I've got two terms under the square root sign. We've got a square. Let's play with trig identities. If I made this 5 sine u, in other words, u is the inverse sine of x on 5, dx becomes 5 cos u. Play with the limits. We're changing them to 0 and pi on 2. So this is what we get. The square root of 25 minus x squared becomes the square root of 25 minus 25 sine squared. But 1 minus sine squared is cos squared. So we have the square root of 25 cos squared, which is 5 cos, multiplied by the dx, which is 5 cos. I get 25 cos squared. Now we have a technique for cos squared. We'll change that to a half of 1 plus cos the double angle, so 2u. Wow, we got something we can integrate. U plus a half sine 2u, substitute in 25 on 4. Fair bit of work there. Of course, I could have done it this way. Hang on, square root of 25 minus x squared, that's just a semicircle. And I'm integrating from 0 to 5. That's just a quarter of that circle. Oh, quarter pi r squared, there's my answer, 25 pi on 4. Recognise the shape and you've got a formula for it, that's going to be the quickest way of doing it every time. Okay? So never forget that idea. Okay, so 4C's substitution, and so note, you're not necessarily going to be given the substitution extension to. If you wish to do it via substitution, by all means, but remember, keep an eye out for, is it in that form, derivative times some function.